Hello. Today I am going to talk about a marketing campaign scenario, which is to predict bank customer response using ML. Let me share my screen so that it will be easier to go through. Today's agenda. I'll go through my background, business goal I'll talk about, and data understanding, models built, model evaluation and tuning, and the next steps. I'm Bhowmick-Saha. My focus is on designing scalable data platforms and AI-driven solutions that not only solve technical problems but also deliver measurable business value, helping organizations make smarter and faster decisions. Now let's go to the business goal. Identify customers who will subscribe to some offer. By accurately predicting which customers are likely to subscribe to a term deposit, the bank can focus its marketing efforts on the most promising leads rather than spending resources on the entire customer base. So here we are talking about increasing ROI. Targeting the right customers means a higher success rate for each dollar spent, directly improving the return on investment ROI for marketing campaigns. Increasing targeted interactions and customer satisfaction. When marketing is more relevant and personalized, customers feel their needs are understood. This is to not only improve the likelihood of conversion, but also it enhances overall customer satisfaction and loyalty. Now let's go to the data understanding. So a data set was provided to us and we worked on it. It is a structured data set in tabular format. Metadata for each column was provided separately with the data for reference. So we did data exploration, we handled missing values, and we did feature engineering. So all these are buzzwords in machine learning approach. So whenever we need to do some modeling to predict something, these are the steps that we typically follow. So data exploration is nothing but it's a step to understand data. In this process, we can query data if we have loaded into a RDBMS, for example, or we can use Python and pandas library to explore data in different ways to check different columns, how the column values are distributed, things like that. We can plot data for different columns, combine columns, things like that, to understand how the data distribution is. In this process, we also figure out how the missing values look like. The more the missing values, the model can become biased because it may not see like the entire picture. Now comes the feature engineering. It is very, very important step for machine learning, and it actually takes quite a long time to do everything. Normally, a data set is comprised of numerical values and categorical values. Now, some of the models can only take numerical values. So what do we do with the categorical variables? We may need to figure out how we can convert the categorical variables into numerical variables. There are different techniques established already to do that. So for example, if in that data set there is a column which can represent a hierarchy, for example. For example, in this data set, we have a job column. And what we did is we converted that job column. So for example, there was a student type of job, or like a blue collar job, or a manager job, things like that. And we have done a hierarchical order starting from like typical understanding of, like, for example, student can be the lowest level in the job, and then maybe blue collar jobs, then maybe technician, then maybe manager, then maybe executive level, so things like that. So there are different approaches to handle, like these kinds of situations. Now models built. So let's start on, for this data set. I'll go through my Jupyter notebook just a little later, but let me tell you that it contains, I think, about 22 columns, which comprises of different features. And there is a label column, which we want to predict. That is the outcome. So, it is about a marketing campaign. So the situation is like the customer will accept the offer or not. So it is clearly a classification problem, and it is a binary classification problem, because the outcome of this situation is either customer saying yes or customer saying no. So regarding the classification models, logistic regression is the most simple one. It is a first simple great model because it creates like linear relationship, linear decision boundaries it can give. It is efficient and interpretable, and works very well when the relationship between features and the target is approximately linear. Then comes the k nearest neighbors. That is another type of model. So this one, if I want to give a simple analogy, it's like finding your friends, for example. If your friends like a restaurant, then most likely I can predict that you will like that restaurant too. So KNN makes predictions based on the local neighborhood. In other words, how similar a new customer is to previously seen customers. It's very intuitive, but can struggle when the data set is imbalanced or when the feature space is very large. So in this case, our data set was pretty imbalanced. The reason I am calling it imbalanced is because we have very few records where the customer outcome was yes versus most of the customers' outcome was no. That's why I am calling it an imbalanced data set. And the feature space is relatively large. It has 22 features. The next type of model is decision tree. So it is like a tree-based algorithm. Think about it like a doctor, for example. When you visit a doctor, the doctor asks you different questions whose answers can be yes or no. Through this, he tries to narrow down what the problem is. So decision trees are very similar to that. They build clear logical rules to split the data based on feature values. They naturally capture nonlinear relationships and handle both numeric and categorical variables without much pre-processing, making them flexible, as I was telling. that a lot of the models need only numerical values. There is another type of model that we considered here is support vector machine, SVM. SVM is powerful when working with high dimensional data. That is when there are many features. It can also create complex nonlinear decision boundaries using kernel tricks. Kernel trick is about finding some important points which has the most importance in predicting the decision boundary. So you can understand that it doesn't need to work with the entire data. While doing the fitting, it finds the most important points that it will consider for the classification problem. So that this allows it to adapt to harder problems, but the downside is that it is very slow. It takes more training times. Let me give little explanation that why I chose this combination. I chose these four models intentionally to cover a broad range of machine learning strategies, from simple probabilistic models to margin-based classifiers. So logistic regression is probabilistic. It can give the coefficients or the probabilities of the weights of the features. It is a great starting point. It assumes a linear relationship and is interpretable, which is always useful early on when you are trying to understand feature impacts. The model 2 was k-nearest neighbors. K-nearest neighbors is based on similarity rather than explicit learning. However, in our case, it struggled because the dataset was imbalanced. The model had difficulty recognizing the minority class effectively. So, going back to the business goal, we try to identify the customers who will accept the offer. So, that is very important. And that is the minority class we are referring to. Decision tree. It is a tree-based learning. It excelled by capturing nonlinear relationships naturally in this case. They allowed the model to make rule-based decisions that reflected the underlying customer behaviors better. Support vector machines. SVM found a good separating hyperplane and performed reasonably well, but it was significantly slower to train, especially on our dataset size. So our dataset was very medium sized. It was not large. So it had like about 44,000 records and 22 columns. Overall reflection, comparing these models helped me understand not just which performed best, but why. Giving the insight into how different modeling philosophies fit the data. Closing thought on ensemble learning. So ensemble learning is something where, for example, you are combining a few models. The models are normally of the same type. So for example, random forest is an ensemble learning. It uses different trees of different sizes and find the outcomes from each model and then combine it somehow internally and gives the output to us. So ensemble learning is also a popular modeling approach. So finally, knowing the strengths and weaknesses of each model helps if we later ensemble them. Diversity among base learners usually leads to stronger, more robust models. Model evaluation and tuning. So now comes using the models using test dataset to see how our model performs. We did not just check accuracy because the dataset was imbalanced. Predicting yes was harder and more important. So that's why we went to the combination of recall and precision. That was the main evaluation metric that we used. We used grid search CV to systematically search for the best hyperparameters across all models. So grid search CV is a keyword in machine learning which you take once you build the model, the base model, then you use it to make, for example, like hyper focused outcomes. For example, your base model gives some outcomes, but maybe the accuracy is not that good, or you at least want to try out what other better models you can possibly build. And grid search CV does that. Basically, it takes the hyperparameters of your model and iteratively use them and fit the data, and then it comes up with the best model while training, and you use it for testing and see how it performs in testing. The model with the best F1 score that we found in this process is the decision tree, and that's why it was selected for final insights. Next steps. So we talked about ensembles. Single models have limitations. Ensemble models can capture different patterns and improve generalization. The other thing is feedback loop, which is almost like humans. It's like learning from its mistakes. Machine learning is not a one-time event. It develops with iterations, very similar like humans. So, real world feedback ensures the model stays accurate as customer behavior evolves. Generative AI integration is another next step that we can explore to see how modern AI systems can augment traditional ML by generating richer features and insights automatically. Deployment is the other thing. Building the model is the first step. And now you have to keep it somewhere so that it can be used for production. So we need to deploy it. We need to create an endpoint, and that endpoint can be called like an API to use it for predictions. Since I work in Google Cloud, I will use Vertex AI that allows scalable predictions, monitoring, and compliance readiness. So this is, again, I did not include it in this session, but I suggest it as my next step. Conclusion. A strong model is not just about accuracy, but about building the right foundation with data. Model comparison gave us not just a winner, but a better understanding of model behaviors. Real success lies in production deployment, feedback, and continuous learning, not just a good offline model. Combining my GCP data engineering background with new AI/ML skills positions me and organizations to drive deeper, faster business value. Thank you for watching, and let me know your feedback.